today. Let's recap what we covered yesterday. So mainly we look around indicators of compromise, try understand how those indicators could be different from an IT system versus an OT system perspective. Why the traditional IDS or detection system might not be enough for cyber physical systems. We also talk about something called indicators of attack. Right, we look into IEC 61850. That is there to kind of help understand the monitoring system and security about the power substation. And we also look into one of the work that we did, developed a simulator where we were able to mount attack, and we were able to derive certain indicators to reflect, to detect some of the attack instances, and so on. Okay, so today what we're going to do is we will look at another work that we did. So in one of the tutorial yesterday, we talked about Ukraine power grid. Yeah. If I just recap what happened is the attackers have gained access to the power system, power substation through control center. So what they did is they targeted one of the operators at the control center, considering that these are the electrical engineers, they don't have enough understanding about the cybersecurity. So the attacker, they send a spear phishing email to one of the operators, and this person intentionally or unintentionally clicked on the link. Now the email was having an attached Excel file, right? So generally, your IDS, the way we design it, the way we rule it, we mostly look for if there are any exe or any malware is there. But generally, we consider MS Word, Excel, like these are kind of more trusted software. Now there are property in Word document and Excel document. They have something called macro. Right? So macro, there you can, write a small instructions, and whatever you want this to happen, when you open the document, it will execute it. So there was macros enabled, and when this person clicked on the Excel document, try open it, there was a Trojan horse attached to that macro, gets into the system, and created a backdoor entry for attacker. Then attacker went to the system, changed the password, and logged him off. So the person who was sitting at that device, he was not able to log in because the password was changed. Now then the attacker, once he or she got access to the device, they look into something called domain controllers, right? So that their next thing is to understand, can they access other devices? Can they access other infrastructure? Now, as we said, some of the infrastructure doesn't have security, so you might, once you are in part of the system, you can access those directly. Some parts may be having some little access. In most of the cases, they do use something called VPN, right, in order to protect kind of sending encrypted environment. But then you can always look into endpoint security of VPN. VPN is from this device to this about. But what about if someone hacked this device and inject the data? So you're sending the malicious data. But anyway, they were having access to VPN credentials, keys to have access, or password have access to the devices, and so on. So they compromised large number of devices. What they did is they updated the software of those devices. We call it firmware here. So they upgraded the firmware. The reason, so the other operators, when they tried to send the command to control the system, it was not working because the software has changed. These commands were not working. But then attackers, since they updated the software, they know what command they need to run. They open circuit breakers, detached generator, transformers, and so on. And they heavily damaged 30 substations and 2 power distribution centers. They also launched telephone denial of service. So they cut down communication lines so you can't report anybody. And this is something happened in real. Yeah? So utility has no idea what's going on, company has no idea what's going on, and it takes around 10 to 15 minutes to do all those things. Now, before they completed their attack, they also run something called kill disk. So kill disk is one of the software. If you run, it will wipe out all your memory, all the storage, right? So if you have intention to look into the forensic, digital forensics, say try understand what happened once the attack is done. There are no footprints, so you won't be able to trace it, what happened actually. Right, so the malware was Black Energy. We talked about that yesterday a bit. That extracts the list of proxy servers in the network. And if you can bypass the proxy, you can get into the system. Right? So we look around this, what to do. So the very first thing that we did is, okay, there's one tool called OLE dump. This is object linking and embedding tool. So generally, if in order to understand whether a macro is enabled in a document, you need to open and check it. But if you open it, there's a high risk if there's any Trojan horse or virus attached to it. So this tool, OLE dump, will help you to understand whether a document contains a macro. If yes, is it enabled or not, without opening it. Yeah, so these kind of tools can help us understand, is it safe to open or not. Then we also kind of look into event logs and host-based monitoring. So we created a tool that can help us understand and detect centralized timeline analysis. So we look into log file access, who is accessing what files, registry data, internal history files. We also created logs for communication network. For example, what time you are stopping and starting a particular activity, acknowledgement status, are there any open connections? Because sometimes attackers also perform some kind of DOS attack where their intention is not to complete the handshake, right? So attacker might send a request, and he send a response and expecting an acknowledgement to complete it, but the attacker doesn't, never send it back. So you have an open connection. You are still, the server is still waiting those acknowledgement to be received, but they never came. Then we also look at some other parameter I'll be talking about in next slides. We also collected some data around attempts of wrong password or change settings of the device. Somebody is attempting to log in, but they are unsuccessful attempts. We would like to know who are those users, how many attempts they are making, and looking around what are the temporal anomalies. Now, sometimes when you collect all this data, it could be because there are fault in the system, there are misconfiguration in the system, there are maintenance going on in the system, there are routine commands that we are sending, or it could be an attack, right? So it's not like when you collect all the data, everything is about malicious. You need to apply some other logic to understand, what happened at this point of time. If you are able to trace it, so that seems it is something legitimate. If not, could be malicious thing. Then we also look at network forensic side and kind of think about how can we improve IDS system. So there's open source called Suricata is one of the intrusion detection system. We try extend that. We use DNP3 protocol, and using Wireshark we were mounting a tag, and then through Wireshark you can monitor and understand what's going on. Then we also look at blocking certain things, so that even your operators are not enough trained, you can still protect their environment in some way, right? So what we did is we blocked the malicious URLs. So generally, there are repositories nowadays. Yeah. So if you wanted to know what are the malicious links so that I don't click them, yeah, Yeah, they're public repository that you can, people are just, whenever they come across with any malicious link objects, they put it there, and then it created kind of a database for us. So we block the malicious URL and masks. We also look into botnet CNC URLs. So as I said, malware gets into the system, and their intention is to send the data out of the network through the control and command server. Yeah, so they send your organizational data to somewhere else, to an external server. And then, of course, looking at more typical IT indicators like IP address and port numbers and so on. We also block some of the malicious object by looking at their hash code. Yeah, so that's very kind of standard practice. Whenever there's a malicious file object, if you're not sure, generally people compute their hash. And then based on the hash, again, we have a repositories of those kind of malicious object that can help us understand what is, because these all are about the strings. What is a virus? It's just a string. It's a code. Yeah. So if we pass this to, if I'm passing the exact code to a hash function, it will give me unique code. So every time, if I have that code, every time when I come across with a virus, I'll pass that to a function. If I get the same code from one of those which I have in my database, I can easily get to know this is this type of virus or malware or whatever. So they are also kind of database and repository. You can also block this. And there's also something called OWASP. What is OWASP? Have you heard about it? Huh? Google it. What is that? What is the full form of OWASP? If we get time, we can talk about tomorrow more in detail. But then at least you should know what is OWASP. What is that? It's OWASP. Sorry? Right. So these are kind of, it's been started, I guess, a couple of years back. And their idea is to think about some kind of standard. Yeah? So they have done a lot of work around IoT practices. What could be the potential cause and cybersecurity for IoT devices? How do we understand IoT architecture? What are different layers and each layer? What could be cybersecurity issues? And then giving some kind of possible recommendations. Right. So you also can do file hash and other things. So as we said, the attackers did use a malware called Black Energy. Black Energy is a Trojan horse that is used to conduct DDoS attack. Cyber espionage and information destructions attack. Kaspersky Lab. So Kaspersky is one of the famous lab in the world. They do a lot of work around cybersecurity. Yeah, they do have their own antivirus, intrusion detection, and other things. But they are very active in research and development. So they look around what happened, and they come across that these are the potential variant of Black Energy. Those were used in that particular instance. Yeah, so they run Windows 32, Windows 64, and so on. Now we also look into, okay, so one thing is how do you, when you are thinking about a solution, the very first thing you need to understand the problem. If you are understanding problem in more detail, you can derive an understanding what kind of solution will work, what kind of solution will not work. Right? For example, if there's a need to protect your data, some kind of confidentiality is needed, we know maybe encryption will work. Now the question is what kind of encryption, and there are a number of encryption algorithms available. Now the question is which of these algorithms will work in that environment, in those conditions. What are those devices? If you are encrypting data on servers, might be there are not much constraints. If you are encrypting data on devices like IoT devices, those devices can't handle a lot of computations. Yeah, and so on and so forth. Sometimes when you are encrypting, data is sensitive, require privacy preservation, and so on and so forth. So we need to build that understanding that out of these, which one will work based on what kind of requirements we have. So we know that we need to apply encryption, but it's not just the encryption. On what system you're applying, how long you need to apply, and what kind of computation you need. Does it support that computation? Do you need storage? Yeah. Whatever computation you are making, do you need temporary storage? If yes, then do those devices have enough storage, and so on. So we collect that requirement of the environment that we are in, and then we decide maybe AES, RSA will not work, and we need to talk about some more lightweight cryptography and so on. Right? So you understand the problem, you understand the environment, so that you get a sense that in this environment we need this kind of, there are restrictions, there are certain conditions, and keeping that in mind, we need to design our solutions. Right? And as a researcher, your aim is to develop a product, a tool, or software, or algorithm, or method specific to a scenario, specific to an attack. There's no need to say, claim that I have developed an algorithm that will, that can prevent all kind of attacks, or this will work in all kind of condition. It doesn't like that. If you're doing so, you are over claiming things. Yeah, these are false claims. And if you're submitting, for example, your publications to top venues, people will immediately reject it. Because there's nobody that can come up with those kind of things where you develop something and then can fit all. It will never happen, right? So we need to understand the problem in that environment, understand what kind of restrictions, conditions we have, and then develop a solution that work in that environment. As long as it's working perfectly, absolutely fine. Right. Now the next thing, when you think about solution, we also need to understand what kind of attack I'm talking about. Right? When we do research, we are not expecting that you consider all kind of attacks and develop a solution and do things, right? Our aim is maybe pick one type of attack, two type of attack, depending upon how much time you have for experiments and so on. But then picking again specific kind of environment in terms of threat model would be good enough. So before we first of all, we understand the problem, we understand the environment, we understand the system model. System model means my problem fits into a scenario between, for example, control center and substation. Yeah, in a transmission system, or my problem fits into between smart meter and control center. So that's a different scenario. My problem might fits into within the substation between different devices, yeah, and so on. So you need to define your system model as well. You can't just say I have developed something that will apply in smart grid or power grid. The system is too broad. We have to be very specific within the scenario that this tool, this solution will work in this scenario. That might work in other scenario as well that you can test if you like. But then when you're designing, you are defining your boundaries as well. Which part of the system I'm talking about, and this is the problem in this environment. Now I'm developing a solution that will solve this problem in this environment for this system or this part of the system. So you define what kind of attack you are considering. Yeah, so we call, for example, system susceptibility, where we kind of assume sometimes. If you're only looking at solution, then you can assume saying we assume attacker will modify X, Y, Z, and then we wanted to know if there's a tool or there's a method that we can come up with that can detect those and so on. So say adversary can perform suspicious and malicious activity, including attempt to access login credentials of the operator and or device, transmission of fake bad commands such as opening a circuit breaker connected to a substation device, and disturbing network communication and packet data. So that's what we assume based on this scenario, what happened with Ukraine power attack. Yeah. So we thought like attacker can do this, because they have default passwords and they have black energy and they can get into the system and so on. I mean, earlier we talked about we have IDS in place, we have a couple of other solutions. Those solutions might be able to detect malware. If they detect it, excellent. What if that doesn't work? And then attackers are really smart. If they have an attack a system with one variant, they are not going to repeat it. They will come up with something very different. Yeah. So they assume might be now you are aware, you have some kind of solution that can stop it. So they come up with a new kind of variant of attack or very different malware. Then we talk about attackers' capability, right? Again, these are very important aspects to consider, because if you are saying attacker doesn't know anything and you are developing a solution, which is okay, but then practically it might be possible that attacker also have some information. If the attacker has additional information, might be your solution is kind of little bit weaker than you thought, because your assumption is attacker doesn't know anything about the system. Yeah, apart from whatever he or she is getting over the network or. So we need to be realistic when you design attacker's capability. What will work practically? What kind of information they might have? So you think about different scenario. For example, if this is an external attacker, might not have information, but generally when you Google it, you collect some, read some papers and write, so you get some sense what devices they might have. Which are, as I said, for these kind of systems, they are very specific vendors. There are 3 or 4 companies. Those develop those kind of devices, and so it's not a kind of very wide world to understand. So might be you go to their website, you got to see what those devices, what their specifications are, what protocol they run. Yeah, you get an understanding whether, and then you Google it whether this protocol has what kind of security it does have, what are the vulnerabilities, and so on. So it gives you a kind of a hint. What are the possible ways to attacking a system, for example, right? So in this case, we said, and the more complex example would be insider threat, where someone within the organization who has enough knowledge how to attack the system, can share system with the attacker, and then they can attack. So depending on capability, say adversary capability. So in this case, we assume that adversary is capable of performing man-in-the-middle attack by altering or replacing a legitimate command, injecting a malicious command, or accessing the control center to send a legitimate command as an insider attack. Right? So you need to define capability of the attacker. Who are those people? Where they work? What the environment? What information they have? And that environment will decide attacker's capability. And then you need to think about what should be the solution. Someone who have access to this lab. So let's say I need to protect my laptop. If there are people who don't have access to this lab, I can put a lock, and I'm good enough. Yeah, my solution is put a lock, good lock. Maybe adults or people with age X can access it. But what if people who have access to this lab become adversary? So the lock will not only the solution, it will not work in my case. I need something else to protect it, right? So it's extremely important to understand attacker's capability. What is the environment you have considered for the attack? It's not just the type of attack, but the environment capabilities, really important. And when we say attacker's accessibility, we assume that adversary has knowledge of the communication network topology, what are the devices I might have, and the way they are connected in the network. As well as power system topology, the adversary also has enough resource to perform the required malicious suspicious actions and has accessibility to the system. So we are assuming that a lot of accessibility information attacker might have. And then you need to think about what you want to develop that will help us, help this scenario. So we derive certain use cases, what attacker target, and how you're going to, what will be the impact on the system, and possibly what action or steps we need to follow. So the use case 1, it says the adversaries impersonate the network and sends a false but unwanted command, legitimate command outside of the control center to breaker of the largest generator. Now, what is impersonation? What does it mean when I say adversary impersonate the network? You're pretending to be a legitimate someone. For example, if you are saying somebody is impersonating director of a company, means you are pretending to be that person. In a way, you are created a fabricated ID in a digital world, and then you are claiming that you are that person, but you are not actually that person. But some way you have created a fake ID that can work. So, in this particular scenario where we are assuming the adversary impersonate the network, gets into the system without detecting, or your device or your ID assumes or understand that this is a legitimate person. Yeah. So, the attacker sends a false command, is a legitimate command, because if it is something unusual command, it will be detected, which is not a part of this routine command. So, what attacker did, get into the system and then sending a legitimate command to control something. In this case, we are opening a circuit breaker of a generator, which is not a routine command. We only do this thing when it's required. When the system seems to be unstable, lines are overloaded, then we make certain actions to balance the system. But in this case, the intention of attacker is to destabilize system, right? Now, we understand what will be the effect of the communication network. So, we have communication network, we have power system network. Under this attack, we can observe and monitor several effects on communication systems, such as we believe we have some kind of IDS in place. Intrusion detection system notifies the control operator what command it receives. Operator verifies whether the command is legitimate. And second, the false command was issued to substation RTU connected to the breaker of the largest generator. So, we assume there is an IDS in place that can help us. Now, it's again depend what is IDS, just a software, simple software, and it works based on the rule that you are putting. If it doesn't have any rule, it won't do anything, right? So, we generally put a rule, what to block, what to allow, and so on and so forth. So, in this way, we are assuming that whenever it receives a command, RTU, notify the notify RTU, saying there's a command which are trying to open something, close something. Yeah. Can you look into this before we execute it? Attacks on the power system. If this attack is successful, we can observe the following impact on the power system. One, insecure operation of the power system. Second, possible shedding of electrical load. If you open something, that means you are disconnecting the system. If there is a demand in a region, if you are disconnecting, you are not supplying it, lines will be overloaded. Right? If lines are overloaded, you are not taking any actions, your components might be damaged, system might be disconnected, or maybe go down. So, we thought in a more detail what are the steps. So, one, attacker targets command mentioned in the threat model. So, we talked about threat model in the previous slide. IDS detects a suspicious malicious command based on its rule engine. Again, default rules, we can put some default rules saying block those kind of IP seems to be suspicious, you can block port number and so on. But in this case, that's not the case, because we assume that attacker sends a legitimate command. But the command was sent from outside of the control center to open something. But you're sending outside of, possibly IDS can detect your IP address and so on and so forth, right? Get a sense that this command was sent by someone who is not part of the network or sent from an external network, and notifies the operator. Operator verifies the control command did not issue this command, right? Now we developed a software, a simulation environment called CPSA, Cyber Physical Situational Awareness. I'll be talking about that in next few slides. CPSA performs power flow. So as we say, once you got data, you pass. Someone trying to open something, close something, you want to run those algorithms to see how this will behave on the system if you allow it. And cyber physical contingency analysis to evaluate the effect of command on the power system if it was allowed to go through. So what if you allow this command, what will happen to the system? So we wanted to, so we created an environment, simulation environment where we can test what will happen to this, and then you decide whether you should allow it or you should not allow it. As I said, even if there is a malicious command, even the data is modified, as long as your system is stable, we are okay. Yeah, we don't really care. Operator discards the command and secure system operation is restored, because since it's a malicious command, operator discards this command. Now, what is called contingency analysis? So saying CPSA performs power flow and cyber physical contingency analysis. What is contingency analysis? What does it do? So in this case, now we are start talking about cyber physical systems, but basically these are physical systems, right? If you take out the cyber component out of it, saying this is all the devices, there's no device which is connected to internet, right? Then it's a purely a physical system. Now within the physical system, your people wanted to know what will happen if component X failed, right? For whatever reason. There's a pipeline, there's a gas pipeline, what pipeline leaks? You need to replace it, you need to block it, whatever, yeah? So from time to time, they perform this something called contingency analysis, which will help them to understand the impact if a certain component fails at any point of time. Yeah, so they do this kind of study where, let's say they have 10 components, they will say, what if component 1 fails, how system will behave, what action you will take, what if component 2 fails, and so on and so forth up to all the components. Yeah, so this analysis is called contingency analysis. Now I'm just talking about one component, so we call it n-1 contingency analysis. You can think of what if any of 2 component fails out of whatever you have. So this is called n-2 contingency analysis, and so on and so forth. Yeah, what if kind of multiple component fails? How does it impact? And so on. So people used to do this for physical systems. Now we wanted to understand how this behaves, how this will work in cyber physical systems. So you start thinking, what there's a cyber attack that targets device X, disable something, modify data, send some malicious command, and so on. So you want to perform that kind of contingency analysis to understand what will happen to the system. Now there is second scenario. We say adversary fabricates or modifies legitimate command sent to a generator breaker over the insecure network. So we are saying the command, let's assume if the command is not legitimate, it's been fabricated. Yeah, someone is sending unusual command. So what will happen? IDS does not detect command modification, but still sends a notification to the operator. Operator verifies that the control did not send this command. CP asks IT personnel or security team, whatever we have, for attack information, with the response that there is suspicious of man-in-the-middle attack. And then you follow the same step as we did previously. In third scenario, so I got one more scenario, sorry. In third scenario, I'm assuming adversary as an insider attack. That could be another person than the operator. At the control center, sends a legitimate unwanted command to the generator breaker. In this case, we assume that command was sent from the control center. Yeah? Not the operator, someone else sent it because they're part of the network and some way they got access to it. The effect of on the communication network, the operator receives a command notification from IDS and finds the transmitted legitimate command was not issued by him. In worst case scenario, the operator ignores the notification and allows the execution of command of the power system. Assuming maybe this command was sent by some other operator. Since it was sent within the substation, might be someone else sent it. Yeah, so they wanted to understand what will happen if we allow it. So IDS, in this case, IDS does not detect insider attack, which is very difficult to detect, by the way, and notifies the operator that this is a legitimate command because it came from control center. Operator notifies that the received command is the same as what issued from the control center, so that seems to be legitimate. Generator breaker receives a false command and trips. So the command is to open a breaker, it will open and detach the generator. CPSA runs contingency analysis, discovers that the system is insecure. Now, not in all cases, but it all depends on how the topology look like, which generator you're opening. So in this case, we are opening breaker of the generator with largest capacity. Yeah? Indicating that command was legitimate but false. CPSA asks IT personnel for attack information with the response that there is suspicion of the insider attack. CPSA prompt operator to reclose the breaker. Right? So if you got to get a sense the system become unstable, then you need to take certain actions. So the software or the tool that we have developed will notify operators, close this or do this. Right? If the breaker does not respond after 20 seconds, CPSA prompt the operator to initiate appropriate remedies, and so on. So that's how we try understand, create certain scenarios, understanding variety of attackers' capability, seeing what will happen if attackers have different capabilities, sending different type of commands, whether it's legitimate or malicious and so on, and what will happen to the system. And then with keeping in mind all the environment, we decided to develop a co-simulator. We call it Cyber Physical Situational Awareness, which is CPSA. Now, the very first question is, what is the need of developing a new co-simulation? Right? Is it possible we could utilize the existing simulators? The answer is yes and no. In a sense, we have power system simulators, we have communication network simulator. What are communication network simulators? Have we worked on any of those? NS2, NS3, yeah, OpNet, the number of communication simulators, and then have the variety of power system simulator. However, we are not having any integrated simulator that can help us simulate the whole environment, including cybersecurity part of it. Even if you try it, some of the simulators are really complex to understand, they are hard to extend, or sometimes they don't really help you in terms of they have interoperability issues and so on. So we wanted to develop something that can be used by the operators sitting at control center. Right. So when you are developing a tool, you also need to think about the interoperability and compatibility with the existing system. If your existing system is, let's say, in Java, everything in Java, and you come up with some Fortran, some other language saying, I've developed a tool, you can integrate it. So integration becomes another problem. So we need to also think when you're designing, developing a product, easily should be able to integrate with the existing system, right? Not develop something too complex so that people don't able to understand. At the end, they will not use it if they don't really understand or taking too long for them. So our aim is to develop software, derive some information out of it, and present that information in a way that operators can understand. Right? If you're asking electrical operators to look into logs and do, run forensic, run Wireshark to detect XYZ, it's too much for them. But they are not trained with those kind of expertise. So you develop a tool that can do things for them, present the results in a way that can easy for them to understand what is happening and what they need to do in terms of taking actions. Right? Right. So this is something called EMS environment. EMS is energy management system, where there's number of operators there, part of EMS systems. And then we have power EMS server and communication. You got a system where you collect and communicate with through communication channels. Yeah. So you go power system metadata and communication network metadata. What is metadata? Okay. What could be example? Right. Yes. 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 Good. Okay. So within power system, let's say at each substation we have something called state estimator. Right. So we can call it distributed state estimator. Let's say. So when you are injecting data, collecting data, sending it to the SCADA. Before collecting, we have some algorithm in place that can look into whether data that we collect looks okay or not. If not, sometimes data could be corrected by algorithm, right? But generally, they are at local level. They are at substation. But what we want to do, we are sitting at control center and wanted to understand what's happening. If I got 30 substation, I'm fetching data from all the substation through RTU. And I wanted to understand whether the data is malicious or not. So we are also interested in developing a global state estimation, right? So what we did, I'll just go in kind of brief detail. We think about power and communication topology. Right. So in this case we created a network, communication network simulation part. So we use in Java. We did system label state estimation in MATLAB, and then we use power word simulator for power system dynamics. We have CPS as setup module, so you can start thinking what should be the setting of the simulator with respect to the realistic settings. So within your environment, you have devices. You can decide what is their baud rate, right? In terms of how fast the communication is, so on. How many devices are connected? So you can represent the realistic, whatever is the realistic scenario. You can map this through some simulators. In a similar way, you decide that I got two routers, the way they are connected. You can fetch communication topology, pass this here. You can have your power system topology, pass it to this, and you can change it at any time, right? If you have change, you can update your topology and so on. We got attack modeler as well, where we believe there's an attacker who wants to play with this simulation tool, wanted to inject variety of attack, and then we wanted to understand how this will impact the system. And then we also created CPSA visualization for the operators. So you derive results, but those results may not be easy to interpret by these electrical operators. So we start visualizing them so that it becomes easier for them to understand. Right, and then we put some logic depending on what are the different cases we consider. We also develop certain matrices. For example, one is called component trust matrix. And then we wanted to understand if there are any physical attack, if there is any cyber attack. We want to trace it in a way, and which components being targeted in a. So you got buses, generator, load transformer, and you say physical, cyber, whatever. Total number of attack, successful, unsuccessful. What was the last time someone hit it, and so on. So you are kind of creating some matrices that can help you. When there's an attack, you can possibly utilize some of those matrices to derive some additional information. Then we have component criticality matrix, which will say which of these components are more critical in a way. Okay, we can repeat the whole exercise that we talk about how you identify critical assets, critical paths, and so on. But in this case, we just try understand if certain assets, certain systems have been constantly been targeted. Those are really critical. From topology point of view, the way they've been connected, the functionality of those assets. So you derive that matrix as well. Okay, so there are a few more things to understand. First of all, what is our aim? Our aim to develop a tool. When someone attack your system, we should be able to understand whether this is a normal scenario, this is an attack scenario. If this is an attack scenario, what is the impact of this attack? If it is a minor impact, possibly we can take certain actions that can fix it easily. Right? So we need to understand this picture, for example, this one, which says this is the normal scenario, first one. The second one says seems to be a slightly issue, but still secure, no issues at all. Yeah? Little deviation, but all okay. The third thing says it's a securable. Seems to be some issues, but if we put some actions, we can secure it. Next, it says it's completely insecure. Definitely need some actions, or might be reconfigure a system, or do some other things. And then last is it's really an emergency. Yeah, you're losing the control of the system. Someone is attacked, compromised several devices, and then you really need a team that can take quickly to take the control back. And then whatever is happening, possibly we kind of try to understand whether it's a cyber due to cyber or physical and so on. Now this is how it looks like. Sitting at control center. From substation you're collecting data. Now we kind of model this. In a way, this could help operators. So the one you see these blue lines, the blue dots, right? These blue dots are communication. They're packets that are being sent from RTU to control center. If the size is larger, that means payload is large. The packet contains more bytes. If the size is small, so through that you also define it. If you restrict saying my packet should be of maximum of 1500 bytes, any packets containing more data could be bigger. If you like, you can also reflect this in different color, for example, a red or whatever. So operators can easily see that, oh, we need to look into this. This seems to me something malicious. So they are not cybersecurity experts, so they are not going to go and check the packet, but they will sit and say, okay, now the packet is coming. Now we are passing this information to the system. We need to observe what happens in one of these situations. Right? Might be they can notify security people saying this packet seems to be suspicious, check it. If there's enough time, they can check, they might discard the packet. If not, we still want to run it to see how it impacts the system. Now when our intention is to utilize this kind of tool in real time, we also need to understand how this, because sometimes demand is different for every day. Right? Demand peak on time, peak off time, and so on. So we also need to understand, let's say, what is the demand in next half an hour. If I'm running this, I also wanted to understand what is the demand will look like. If you're considering the demand is constant, something goes wrong, you start sending certain commands to balance it, right? Which is not correct. If in the next half an hour there will be an increase in the demand, suddenly you see there's a spike and you start thinking, oh, this is an attack, and you start like, however, this is not an attack. This is the projected requirement in next half an hour, right? So we also need to understand what is the And that's why we say future demands scenario, this one, yeah. Evaluate system behavior with future demands. So you need to understand what is the demand, what will be the demand in next half an hour. So you project that this will be the load, this is how the system will look like. And then you understand if that doesn't behave like this, what will happen. Yeah, what's happening, is there an attack, and so on. So in this case, let's say if we are saying 30 iterations. So let's say I come up with a tool that I can run every minute. I can, in a way, feed the expected demand for half an hour, run that environment. Yeah, and I'm saying my software runs every minute, so I can do 30 iterations, saying this is how it looks like. In the next half an hour, I can derive the results. This is how they look like. And as you go in real time, you can compare what you are getting with the one you have computed. If they are expected close enough, you're okay. If they're not, something's wrong. All right, so, okay. For a particular scenario, what we did is we run the simulation for 40 seconds with 8 time step, 8 iterations, considering the software ends for, one cycle ends for 5 seconds. Yeah. So you run 8 iterations of it. So we were deriving, as an outcome, we were deriving certain Excel files and some other things, and then plotting those results through some graphs so that electrical operators can actually understand. Oops. So this is how it looks like, the interface that we created. It's a simulation environment between control center and RTUs, which is substation and control center. What is the baud rate? What is the propagation delay within the network? Number of packets that we have sent, whether and what kind of packet it is. Is it a data? If it is a data, that's been sent from RTU to control center, right? If it is a command, being sent from control center to RTU to substation. What is the packet size at control center? What is the packet size expected at RTU? Then we created a tab called operation. So you can simulate normal operation. You can run this. This is normal scenario. These are my results for normal scenario. If you need to inject attack, you can pick single attack, and you can pick any of those attacks. So we simulated 4 different types of attack. I'll talking about them. So you can say single attack, pick one of the attack, and you also decide what time it should jump in. So if I'm running a cycle of, I'm running 8 iterations, I will say after 3rd iteration, at 4th iteration, I'm injecting an attack. Let's see what happens. Yeah, so you have some understanding that first 3 iterations will be okay, but then starting at 4th iteration, we are expecting some deviation. So for example, we talk about bad command injection attack. We simulated bad data injection or false injection, whatever you call it. RTU DOS attack and delay attack. Delay attack is, for example, you're getting data, but data itself is delayed. Yeah, you consider topology, and you are, in a way, collecting some logs. Right? So in a normal scenario, control center sends command to all the substations. So I think in this case we consider around 12 substations, if I remember correctly. So you are sending a poll request. So polling means you are requesting RTU to send the data, right? So everything is done in a command way. So control center sends a poll request, a poll command to all the RTUs at substation, and expecting them to send their data at this point of time. So what RTU will do? Through sensor, they will sense current measurements from the devices, send back to the RTU, and RTU send back to control center. Right, so you can kind of create a log in terms of control center, this port connected to this substation, this RTU particular, at this time. So you have kind of what is the size and everything you can. And in a way, you can also derive how long it takes to send a packet or to receive a packet. Again, they are not constant. They are not always constant, but you can get a sense between this and this. It takes roughly 2 minutes, roughly 10 minutes. Yeah. And this is the normal scenario look like. I'll be talking about that in other slides. So we run the normal scenario, try to understand how the system should look like for the next half an hour, let's say. And then we start thinking, okay, what if we inject bad measurement, false data injection attack, where you fabricate data, pretending these are the current measurements, and then feed it, send it to the control center, considering, let's say, RTU is malicious, for example. Someone compromise RTU. So there are different ways you can think of. Someone can compromise your sensors, can modify data, send it back. Or if sensors are correct, someone can compromise RTU and modifying data at that point. So attacker manipulates raw measurements at RTU. In this case, that's what we thought. RTU sends bad measurements to control center. IDS and DSE provides an alert of suspicious data. May or may not, depends on how much you are changing in a way. Right? If you are changing the data, but data is within the threshold, might be your IDS won't pick up. If you are changing certain chain, maybe IDS can say, oh, this seems to be suspicious because we are not expecting that much payload, and so on. So as we has an attacker module, at this one we decided to pick an RTU between this and this. So what data you want to change? So we want to change, for example, either you can change the generation capacity. So you can reduce the capacity, you can increase the capacity, you can change in load. You can say in this region there's a more demand, so you can increase the load. You can open circuit breakers and things like that. So you can pick particular, in this case we are talking about data and false data injection, so we can kind of change magnitude of voltage, current, active, reactive power, and so on between whatever you like. So we want to kind of run some simulation environment, derive some results. For example, without bad data injection, with bad data detector. So as I said, state estimation by default has some capabilities to correct data up to a certain extent. Then we see normalized load profile and profile under attack. So the yellow line is kind of giving you what is the expected load profile in a normal scenario. But then when you're injecting data, maybe increasing the load or decreasing the load, it kind of behave differently. So through those kind of graphs and figures, you can derive your understanding whether the system will, what kind of impact it has on the system, and whether this seems to be stable or not. The second scenario, where we talk about malicious command injection. So again, we talk about 3 different cases. By assuming there's someone sends a malicious command to open or close circuit breakers. So attacker intercepts a legitimate command, alters it, so that could be the case. IDS identifies bad command based on its rule and notifies to the control center asking to confirm whether you are the one who sent it. Now this kind of tool can really help in those situations. When RTU receives a command and it's not sure, wanted to confirm whether the command is legitimate or malicious, and you don't really have time, because in few seconds, few minutes, you have to, as an operator, you have to make certain decision. And sometimes it's not easy to confirm whether the command is malicious or legitimate. So what we can do, we can pass this command. As I said, we have the exactly same environment. You have all the parameters that you have in physically. You can pass this to this software, and you have exactly the same environment. So you can decide on what if we allow this command, what will happen to the system. You run that simulation, see how it behaves, and then in real. So as I said, just run in 1 minute cycle. So in 1 minute, I can run the iteration, get to see how it will behave, And then you can decide whether you want to allow it or you don't want to allow it. Right? So in this case, what we did, so say IDA suspects a bad command. What do you want to do? Do you want to reject it or do you want to simulate it? I'll say, okay, if you are sure that this is legitimate command, no problem. If this is a suspicious command, you are sure, you want to reject it. Say, oh, this is not allowed anyway. We only use this command in emergency, for example. So you directly discard it. If you're not sure, you want to run this. Say, okay, let's simulate and see what will happen. So you pass this again. In this case, we have, let's say, change generator status. So we are opening a particular generator, right? And then running this command. Run this command, the whole process. And in this case, we are computing something called aggregate megawatt contingency overload. So there are some particular power system parameter that you compute, and those parameters will help you to understand whether things are stable or not stable, right? So you compute that parameter, run that algorithm, get a sense whether you want to finally reject. If you think that these values is way beyond threshold, definitely it seems to be suspicious, you want to reject it. Say, I have simulated, I don't want to run this command over the real system. So as an operator, you can discard this command. If you think it's very close to what you're expecting, it seems to be legitimate, okay, so you want to say allow it. When you do this, this will be run over the real system. It will open the generator, the circuit breaker for the generator. Right, we'll take 2 more minutes. Third scenario where we are talking about there's a delay measurement. So what we said, sitting at control center, you are fetching data from RTU and then passing it to SCADA system, running an algorithm. What if you're not receiving data from one of the substations? The data is delayed. You're getting, but maybe you're getting too late. You're getting data from all other RTU, but then there's one RTU not sending data in the time you're expecting. You can't really wait too long just to wait, but you just simulate and see what will happen. So what if the delayed measurements are delayed a bit, right? How they will look like. So you kind of start plotting things, do some experiment. When you say delay, how long the delay is. You know, if the delay is slightly, it might not impact. If delay is too much, it might impact. So if you don't feed the data, or if you are assuming that data is very close to the one you received in the past, so you are assuming that this time the data kind of very similar, and run and simulate. But then when you got the actual data, you run again and see the difference. So this will also help you to understand what is the delay tolerance there, right? If you don't receive data, how long your system seems to be stable? Because we are relying on the previous historical data, the data that you already received in a way. And the last scenario where you assume disable RTU, you're not receiving any data, there's no delay, you're not getting any data at all from one of the RTUs or from number of RTUs, for example. So in that case, you don't have understanding, so you are losing the observability. You have no understanding what's happening at substation X because you're not getting any data, right? So we run those kind of things to understand what does the situation look like. Is it the emergency, the graph that we have seen? And then we put some other logics to try understand the observability from some other way through other substation and so on. Yeah, so for example, in this case, we lose the observability in this part, the brown one that you see in dark. And then we are trying to understand what is happening there because you're not getting any data from that. So for example, it's a legitimate versus malicious command to open generate number 36. So we open the last one. So the generator was closed and then we just open. So these are kind of logs and the outcome that we have created, stored into certain files and so on, and then plotting those for operators. These are the power system quantities. So like you got buses, you got generators, their capacity, transformers, and loads, and other things. We are also kind of keeping, as I said, log on communication side. How many routers you got, what time they're sending packet, what is the size of packet, and so on. And you derive certain matrices, system susceptibility, access point matters. You know, what kind of attacker made, what device they have access, which port number they have access, threat capability matrix. So you have security team that can detect some of the packets and so on. So this kind of, you are creating historical data for you to help understand which part of the system is critical, which devices are critical. You know, because they've been constantly been attempted by the attacker. And I guess this is the last slide before we go for break. Try understand. So when you run this malicious command, so in this case we run the malicious command after iteration 4 onwards. You see, so this is the load profile. So we say in the next half an hour, this will be the demand look like. It will go up in 10 minutes and then whatever. This is the normal scenario look like. And that this is the one when you perform an attack, detach a circuit breaker, you see the expected results slightly vary from that. Right? So this kind of, and these are the graphs possibly your system operator can look at. Because they're looking at the big screen, all kind of block, you know, and the kind of power system I shown you. So they're looking at all those things to understand what's going on. And at point when they think things are not correct, they want to investigate it. So we did this with the for the US Department of Energy. Let's have a 10 minutes break. We'll come back and talk about some other things. So we can start now. Okay. Shall we start? Okay. Right. So we want to look around the another topic. So let's change our direction a bit from just not just looking at smart grid, but also thinking about, for example, electric vehicle side of it, or understand vehicle side of it, and then we'll talk about a bit more around it. So one of the work that we did, one of my students did, is around vehicle theft. And the reason is, if you look at this, which says vehicle theft in India double within a year. Delhi, Chennai, Bangalore among the most theft prone cities. So vehicle theft is one of the key problems, right? Not just in India, around the world. So it says 47% of all stolen cars belong to Maruti Suzuki brand for some reason. And it says like around 80% of the stolen car, kind of this incident happened in Delhi. So 80% of the incidents of vehicle theft happen in Delhi, but then Chennai and Bangalore are also among those cities, part of it. So it's last year information. Now in terms of we see what happened in the UK, according to UK police statistics on auto crime, there were over 129,000 auto theft cases in England and Wales, 23-24. When I say England and Wales, what does it mean? So it's according to UK police statistics, X number of cases in England and Wales. What does it mean? What is England? What is Wales? What is UK? What is the capital of UK? London. What is England? State in UK. Okay. And Wales? So UK is a country. It's a United Kingdom, right? So earlier they used to have 4 countries. One country is called England, other is called Wales, there's another called Scotland, and this other is called Ireland, right? Now people of Ireland, so it's a North Ireland and South Ireland. People of Ireland should decided that they want, so they were a kind of, okay, so England and Wales, they come together and then we call it Britain. Yeah, people from England and the region from being England area and Wales, it called Britain. Then Scotland merged them, joined them, it becomes Great Britain, right? And then in Ireland, North people start saying, oh, we want to join them, and then people from South they don't want to join it. So the south of Ireland is called Ireland by default, and then north part of Ireland becomes part of UK. So when you say UK, you're saying United Kingdom and Northern Ireland. So United Kingdom, by default Scotland, England, Wales. We are talking about these 3 countries, right? And then northern part of Ireland. So that becomes kind of UK. So it's a country, consists of countries, right? So it's talking about two reasons of it, England and Wales, not everything. So the reason of vehicle theft is saying exploited vulnerability include increasing acceleration remotely. So I'm not sure if you heard, but there are several stories published by researchers, hackers who are able to hack vehicles. Even when the vehicle is in motion, they were able to control brakes, increasing acceleration, opening doors, kind of turning on wipers and so on. So in this case, you see the increased acceleration remotely disabling brakes of the vehicle, access to air conditioning, lock doors, data injection through telemetric systems. And in 2014, thieves stole 6,000 vehicles using keyless technology. What is keyless technology? You can lock unlock car, yeah, remotely. You get remote and then you those keys. Either you have physical keys that you turn it to lock unlock, or you have a remote keys. So remote keys generally work on some technology. It could be RFID, or it could be Bluetooth and other things. And those technologies have some kind of cybersecurity issues within those. So which make it half of all vans and vehicles stolen. So in year 2014, there were around 6K vehicle of with keyless technology were used, and there were half of them were van. And with top of the range vehicles such as BMW, Range Rovers, making up 70% of the vehicles stolen. So vehicles are more particular around what kind of model and what type of car they want to steal, because it has certain issues, security issues within those. So do you understand how does it work? How does your car work? What are the components it has? There's something we'll call CAN bus, yeah? Control area network. So you got a bus system, and then there are several components which are connected to the bus. One of the component is, so we call this CAN bus system. So by default, when you are driving a car, your car is collecting some data internally, yeah, so that it can derive whether everything looks okay or not. Because there are safety system in this, which always checks if certain values or parameter goes beyond the expectation, it will put some emergency brakes or some other things, right? Emergency, for example, airbags and other things. If you are speeding up, and now earlier we were not having those kind of features, but now cars are really smart. They can guide you the lane, so you can turn on the lane. There are sensors, always track lane as the route moves. They will guide you, turn this, so slightly. They will, if you are moving a little bit over the line, it will help you do things. There are sensors that can look into the speed, so they detect the object in front of you, and then how fast you are going. If you are going too fast, it will show up some warning. If you don't stop it, it will stop by default. So there are cars with those kind of advanced features that somehow avoid collision. If you're too fast, they will suddenly, emergency brake will be applied automatically, that will stop your car. Yeah. So this can only happen when when your car is collecting some of your data. You collect it and then process it. If your vehicle in front of you is of X distance, what is the speed of you? How much time it will take for you to hit that? If you're not, and it waits for certain amount, few seconds, up to few minutes, depending on the thing, for you to take action. If you don't take action, the machine itself take action, yeah, to avoid any kind of collision and incidents. So we have several variety of those things within the system. So we have something is called electronic control units, ECUs. So ECUs are kind of a storage or registers. Those store all these kind of values, as I said. And they always check those calculations. So it's a CAN bus is a multi-master, multi-slave, half duplex, and fault tolerance protocol. So we talked about the other day what is master and slave model. What is half duplex? Right. So it's a two-way communication, but you can do it one at a time, right? So if somebody is sending, you can't send it. You have to wait. So that's half duplex, and then you have full duplex where you can send at the same time, right? Fault tolerance, we wanted to understand when the system is fault, can we still continue? Especially in this case, if you're driving, if you're going to a highway, suddenly there are some issues in your system. Now, at that point of time, depending on what is it possible for you to continue with that or not really? Yeah, so they wanted to develop those kind of systems that can guide you what is wrong with the system, right? And that comes with a cost. Yeah, more advanced car means more smart, advanced features that can guide you things, not just in terms of fancy where you can turn on heating and AC and this and that, but also in terms of automating process to help you, to guide you, to keep you even better secure and safe. So we got CAN high and CAN low lines. So as I say, ECUs are the component that control a specific function in a vehicle, such as your engine, your brakes, steering, and they are the processing unit. Then we have something called BCM. They look for the body parts of the vehicle, for example, doors, windows, mirrors, lighting, and so on. They all are remote. When you press the button, gates open, windows down, and so on. All those happen because they are registered ECUs, BCMs are there that are changing the state. Right. Then you got HVAC, which is heating, ventilations, air conditioning, to keep you kind of whatever temperature you like. You can set the temperature, you turn on the air conditioning, and so on. And then you have instrument cluster, which is a dashboard that you see that shows your driving information, for example, speed, what is the RPM, what is the fuel label, what is the current speed limit, temperature, and so on. And this is how it look like. There are a number of parts now. As these vehicles are getting smarter and smarter, the technology itself getting more complex to understand. Right. So if you see this, the number of things, LED lights, your hydraulic brakes, keyless entry, dashboard, climate control, diagnosis unit, power steering, engine control, and then so many variety of things. So there are subsystems within the system. If you look at the right side, you got exhaust system, you got support system, you got engine, steering system, powertrain, electrical system, coolant system, fuel system, brake system. So the number of systems, if any of those got fault, it has direct or indirect impact on the vehicle itself. Right? And now what we are doing here, we are making things smarter. That means these systems might be talking to each other, subsystems. And if that is something happening, then definitely we need to think about. And then again, your car is not just collecting data within the car, but they are also sending it somewhere else for company to process and understand. Right. So in the future, we are also expecting something called connected vehicles. So the concept of connected vehicles is your company or remote side unit, they are collecting the information from all the vehicles, processing it, controlling, for example, traffic. Yeah, they're processing all the data from the region and then possibly guide you rather than this is the better path, rather than going here, there's a lot more congestion, follow this. So they're sending some kind of signals and for different companies to understand. So they're collecting data from you, understanding what's the environment, processing it, and then guiding you in a way. So again, this all involves some level of cybersecurity issues are there that we need to fix. Now there's something called OBD, onboard diagnostic system. So what happens when your car has some fault? What do? You go to garage, you go to a mechanic saying, oh, my brake light is, something has happened, right? My brake got failed, or I'm having this kind of signal. After every minute, my car getting off, or so on. So depending on what's happening in the system, what they do, they have some kind of software. I'm not sure how does it happen here, but in the UK, we have these people have the kind of software that, and then we have an OBD port in a car. So OBD port is the one. So as I said, car is collecting some of the data, they store somewhere, and you can access that data through OBD port. So they're connecting their device with that port in your car, and generally that port is near the driving seat or so, and they run some to see whether your brake system is okay, where your powertrain system is okay. So they look for all the substation and then subsystem and go get a sense that, oh, this seems to be something. So start showing some fault errors code, and if you interpret those code, you get a sense what is wrong with the system. So OBD refers to automatic electronic system that provides vehicle self-diagnosis and reporting capabilities for repair technicians, right? OBD gives technicians access to subsystem information for the purpose of performing, monitoring, and analyzing repair needs. So it gives you some kind of codes, and you interpret code and see what are the issues, and then look into how can you fix it. So it can track wear trends and see what vehicle parts are wearing out faster than others, instantly diagnose vehicle problems before they occur, supporting proactive rather than reactive management, and measure driving behavior, speed. And now, when you go for insurance, for example, I'm just talking all the scenario from the UK because I have no understanding how does things work here. So you can relate if you have that understanding. So if you are going for insurance, right? If you are a new driver, you just got your license, yeah. By the way, in the UK, you have to clear it. You have to drive in the city to get it. So it takes time to get your license. But once you get a license and you want to buy a car, and then of course you need insurance. So the variety of insurance, what you want, do you want only third-party insurance? In case of incident, you want to cover the other person, vehicle. You want your as well? So that's more comprehensive. That will, in case of incident, that will cover your vehicle and my vehicle as well. And insurance also says why, what is the use of your car? Are you going to use it just to commute, going to the market, blah, blah, blah? Are you going to commute this for work purpose? Are you going to commute this with other cities? Are you going to go other cities using your car? So depending on the kind of boundary, your insurance amount is being decided. Now, in order to if you are a new driver, the insurance generally is high, much higher. And the whole concept is if you don't hit it, next year your insurance get down and down and down and down. As you become more efficient, they believe there are less risk of accident, so your insurance amount is down. For new driver, it's really high because they have no idea, they can't see your track record. They have no idea whether you will be able to drive it safe. You got your license, they have some trust, but they don't know really whether you are still have that level of skills. Yeah. So your insurance is high, and every year as you, without hitting the vehicle, you manage it, your insurance get down. So for the newcomers, they also have for people up to few years. But then they have something called, they got some device, and they say, we can lower down your insurance if you put this device in your car. While you're driving, this device will send us some data. Now the data that they need is how you are driving, your driving behavior, right? And then look into when you are at sharp turn, are you really making a sharp turn? Are you you are putting sudden brake, things like that. How often you are changing your gears, and things like that. So they're collecting a lot of information to understand your behavior. And at any point, if they see, and obviously they are tracking you. If you got to get your insurance, let's say to cover a specific region, if you go out of that region, insurance doesn't it doesn't cover. But then it can also kind of give you notification that you're out of that region and so on. So somewhere they are collecting some information, try and understand your driving pattern. If you don't want them to collect that information, then you have to buy other. There's also other type of insurance, but they are much costly compared to this one. Yeah, so in some sense, there are companies collect data and they use it for whatever purpose, and so on. Now, what is the need of this OBD? So again, we look at the history. It started in 1968. First OBD computer system with scanning capability was introduced by Volkswagen. This is a vehicle from which company, which country? Can you Google it? It's a German guy, yeah? So it started in 1968. They thought maybe there's a need to have OBD port. We should be able to scan the vehicle, especially when it's running, so that we can, and that will also help you to understand the faults when when something goes wrong in the system. And after 10 years, 1978, Datsun introduced a simple OBD system with limited non-standard capability, because at that point of time there was no standard how vehicles should be manufactured and so on and so forth. 79, there's a Society of Automotive Engineers. They recommend a standardized diagnostic connector, and they say all the vehicles should create their own OBD ports as per this standard, similar to this. 1980, GM, which is General Motor, introduced a proprietary interface protocol capable of providing engine diagnosed through RS-232, which are cables. Interface, and more simply by flashing the check engine light. So even in the older time, we had some kind of solutions. Most of these solutions were proprietary in nature. They were hidden kind of. They are very specific to manufacturer to manufacturers. They are not generalized things. 1988 standardization of onboard diagnostic came, and 1988 SAE recommend that call for standard connector set of diagnose. 1991, so this actually started implementing in the US mostly. So from 1991, it started getting more popularity. State of California required all vehicle to have some kind of basic onboard diagnostics. Yeah, this referred to OBD1. And then 1994, again, they say they make it mandatory. After 3 years, saying this is mandatory. If you're a manufacturer, you have to have this one in the cars. So 1994, State of California mandate that all vehicles sold in the state, starting in 1996, must have OBD as recommended by SAE, which is your Society of Automotive Engineers. Now referred to as OBD2 or second. This stems from a desire to perform across-board mission testing. This includes series of standardized diagnostic trouble codes. So they standardize this. For every kind of fault, they give some kind of code, so that by looking at code, people can get a sense what is happening, and kind of keep it more standardized. So every manufacturer, they should follow the similar practice. So your codes are not vehicle specific or manufacturer specific, rather they are more generalized. Irrespective of the vehicle, once you got to see this code, means this error. Yeah. 1996, OBD second becomes mandatory for all cars manufactured in the United States. So earlier it was just the state of California, but then 1996 they applied it countrywide. 2001, European version of OBD came, becomes mandatory for all gasoline vehicles in European Union. And 2003, it becomes mandatory for all petrol diesel vehicles in the EU. 2008, all vehicles in the US are required to implement OBD2 through CAN, Control Area Network, CAN bus system, specified by. So they release some standard, and they say you have to have OBD, you have to have CAN bus with this standard, ECUs and other components. The whole point is there are variety of manufacturers, not just in the UK, around the world. We import cars, we export vehicles, and if they are following the same standards, it becomes much easier to understand the mechanics, fault, and how you fix them. And whatever parts are being made, they are also kind of more generalized. You can use them. So one of my students were looking into kind of similar work of vehicle theft. So we pick up a data set, and the whole point is, so data set is around like 10 drivers driving a vehicle, collecting data set, and the whole point is if someone get into the system, start driving it, is it possible to identify that this person is not one of those drivers who usually drive this car. Yeah, so they apply machine learning, range of machine learning algorithm to profile the drivers. So you profile each of the drivers, and you consider the attack case in an intruder, who is not the actual driver. And then some of you try to see, in a way, this doesn't belong to one of these. So you do some cluster analysis or whatever. So in this case, he looked into supervised and unsupervised based learning to derive some classifications model, and then kind of comparing whether this driver belongs to one of those pools of drivers or not. Oops. Okay. Now this was the typical process of vehicle that we have. Now we are saying gasoline vehicles. Now there's a noise around electric vehicles. Yeah. What the people are saying electric vehicles are better because it reduces carbon emissions. And nowadays we are saying there's a hybrid vehicles coming these days. What is a hybrid vehicle? Generally, it says any vehicle which combines two or more source of power. Yeah, so diesel, electric. So generally people have petrol, diesel cars, then they got CNG, so you can run with CNG as well as petrol and so on. So in a similar way, you might have diesel and electric, petrol and electric, gas or electric. Two power sources found in hybrid vehicle may be combination in different ways, either in parallel or serial. Now it depends on, when you're driving your car, can you use both type of source of energy, or you can use one at a time. That we are calling parallel and serial, right? So for example, this is the example of parallel. So you go gasoline motor, and then batteries will power some electric motors. Both can power the transmission at the same time. That's why I'm saying they're parallel. So you can decide on whether you want to run your vehicle on battery or on fuel or gas. If you are able to do this at any point of time, we call it parallel. So the system is designed in a way at any point you can switch. Right? Electric motor supplements the gasoline. The other example is serial or series hybrid, where you can active one at a time. Gasoline motor turns a generator. Generator may either charge the battery or power the motor. So let's say if I'm running with fuel or gas, I might charge my battery and then driving. After a while, when I see my vehicle, my battery are charged enough, I can use it. The kind of vehicle that are coming, especially in India, hybrid vehicles. I don't know if there's any pure electric vehicle came so far, but most of the vehicles are hybrid in nature, which says for lower speed, is powered only by the electric motor. And so, so you have that provision. You can run with your battery, start driving your battery. When you think the battery is going down, obviously battery has their own life, how long you can drive. So if you're going from, let's say, Delhi to Mumbai, it's a long route. Might be start driving with your battery. After a while, the battery goes down, so you start driving with your fuel. At the same time, you're also charging your battery. Yeah, so when you charge your battery you possibly want to switch and so on. Or sometimes they have a kind of those restrictions. You can, because battery can't support much, so for local or slow driving, you can have battery, but then if you need to go farther, just go for fuel. Okay, so we talk about all those things. So generally, we have more than 80 ECUs in the car, so collecting different type of data from your, steering, brakes, and so on and so forth. so many things. They do have navigation, so connecting to GPS. Yeah, the kind of GPS that we have is from US. Yeah, global positioning system. India is also developing its own. I don't know if you know it. What is that called? Navik, right. They said there's a threat. What if if there's a war between US and India, and they start misguiding you with GPS, because you're relying the position with that one. That's why India started developing their own. Okay, look at how this evolved. Early CANs were wired. There was kind of small few components as a closed circuit. More recently, CANs contain wireless components. And now once you have wireless component, you can remotely control things. There's always a cybersecurity component to it. So some people, the researchers have run some experiments, and one of the experiments is they wanted to understand how safe the modern car is. So again, it's a 10, 20, it's like 15 years back. They did some study. So the experiment was done at University of Washington and University of California in the US. They picked few models, car models. They wrote a packet sniffer. Packet sniffer generally used to create a fabricate packet. So you create a fabricate packet and inject it in the car to see what will happen. So when you are hacking, you do those kind of things. Introduced into CAN bus system by simply plugging a device into the car federally mandated OBD port. So what they did, they connected a device with the OBD port of the device and inject some malicious data to it. So this is kind of assuming that you have access to OBD port. But there are also researchers, they have done study by remotely controlling the devices, controlling the brakes and opening the gate and things like that. So they did some kind of, even on Tesla and other vehicles. They used fuzzing to emulate the command that car respond to. So it's kind of systematically they wanted to understand when we do this, what will happen to the system. And using the command, they discovered, they performed live tests to see how much the car they can control, what happened when there's malicious data in this. So the results were researcher could not only fully control the car using their device, but they could also control the car when car is in motion. So for example, with 40 miles per hour. Yeah, so car is moving at 40 miles per hour, they are still able to control the car. Now that case it definitely has a life-threatening scenario, not just for the person who is driving, but people on the road, other cars and so on. Among the things they could control, they were able to disable brakes. They were able to engage brakes. Suddenly, there's a high sudden brakes. Disabling Y ports, continuously spraying fluid to wipe it on the screen. So the driver, you don't really see clear things. Permanently activating horn, killing engine. So the sudden fail of engine, your vehicle will down. Unlocking doors. Yeah. So they were able to do all those things. Also found that they could write programmatic commands and viruses that would activate certain conditions. For example, disabling all lights when you are at certain speed. Brake the car when you are 100 speed. So when you are 100 miles per hour, you don't put sudden brake. If you do this, it will damage your component. It might damage your component. Yeah. And so on, because the vehicle behind you might not be putting sudden brakes, and they might hit you as well. Even though they had physical access to the CAN, they noted that some commands could potentially be executed wirelessly. So in this scenario, they assume that they have access to the vehicle to the port and where they connected their device inject. But then some of the devices are working wirelessly, so they can also control those devices remotely. The problem with CAN system is not secure. Your data, they're collecting data, but the way it's been collected, the way it's been stored, is not secure. Every message is an unencrypted plain text broadcast to every device on the CAN. As I said, all these physical devices, electrical devices, mechanical devices, they were not designed with the security in mind. So they don't generally work with TCP/IP models, but they work more on lower level, layer 2. The devices, they can talk to each other with number of different protocols. And those protocols have by default several security issues, vulnerabilities. Now we are start calling those vulnerability, but these were not vulnerability until people were using them physically without internet, right? Because they were not designed with the security in mind. That's why they are open vulnerabilities. Now people from cybersecurity, they think like, oh, these are vulnerabilities. However, actually these are not vulnerabilities. They were not designed with that one. If somebody has designed the software with security and then you are able to identify weaknesses, then you can say these are the vulnerabilities. Anyway, so the possible messages and communication procedures are often documented and made. So again, as I said, those systems were more proprietary in nature. So every manufacturer is coming up with their own kind of solutions, which is hidden, which is not generally available. But then as time moves, people will start publishing things, and so those can give enough ideas for people how to hack things. Again, there's no component authentications. So there's no way when a device is sending a data or command to another device, there's no authentication. Anyone can send it. And as I said, in most of the systems, what is the process is you broadcast the request. Whoever responds faster is being considered as a response. Every other response has been discarded. So as an attacker, if you can send a faster response to the device, your response will be accepted, and actually the response from a legitimate device will be rejected. So a device can send a command to any other device. Attacker could use, for example, tire pressure gauge to turn off brakes. So they can control one part of the system for another part of the system, and so on. Solution. So people start looking into security flaws, particularly wirelessly communicating ECUs, and start thinking how you can put some kind of authentication. So something is called controller authentication is there. Only valid controllers can communicate to CAN, and that's what you want. It should not be like, even if people are able to connect their device to OBD port, it should not be like they are able to inject it. There should be some authentication process in place that will ensure that user or device is actually the legitimate device. Must be high performance, use symmetric key, and distribute symmetric key using asymmetric encryption. What does it mean? So which is faster, symmetric encryption or asymmetric encryption? Symmetric encryption is faster. Why? Why? First of all, symmetric encryption, the key size is small compared to asymmetric. So if you are using RSA, the key size is at least 2048 bits. If you are using AES, it's just 256. Yeah. Secondly, for a larger system, the number of kind of the packet that you encrypt and decrypt, the whole process has become much faster. But then the problem with symmetric, you have to send the key over the network. So one way we've seen like Diffie-Hellman key exchange, but then but not every time we want to create. And then we have seen that there are authentication issue with Diffie-Hellman. Yeah, there could be man-in-the-middle attack that can create two connections and generate the same key. So the best way is you apply encryption with the symmetric key, which is faster. But then you have to send this key to the recipient. I can use asymmetric encryption for the key. Yeah, so I can encrypt the key with the public key crypto system, send it to the recipient. Recipient can apply their own private key to decrypt the key. And once you got the symmetric key, you decrypt the message. So for encryption, you use symmetric. In order to send that key to the recipient, you use asymmetric. And this concept is very popular, very widely used, whether you talk about payment systems, whether you talk about email security and so on. So whenever you need to send the key, we always use asymmetric environment. Whenever we need to apply encryption, mostly we go for symmetric. So that's how you balance trade-off between security and efficiency. Okay, they got firewall, restrict the component commands to only those essential to its function. So you have to apply some sort of firewall in place that can restrict what can be done, what cannot be done. If something goes, This is kind of a software can flag you when someone try to do something which is against the rule. So it says the automakers or the car manufacturer need to understand the seriousness of having network car component and take security measures accordingly. These security flaws are growing in seriousness as car automate more and more things. And now every year you see there's a new variant, new model of a car that can do something fancy. Yeah, remotely you can do this and that, the new things. There's a voice assistance in the system, automatic lights, and there's so many things. But then there's a lot of insecurities in that. With the emergence of Bluetooth connected ECUs, this is a serious security issue that cannot be ignored while longer. So there's an entertainment system. You can connect your own car, your own mobile phone. You can connect these smart devices, and so on. But then they're all done by Bluetooth, but we don't know whether the Bluetooth contains enough security or not. So I'll talk about some statistics very quickly. So particularly in the UK government is pushing EV infrastructure really a lot. They want by 2050, 2040, I guess, they want to replace all the gasoline and fuel-based vehicle with electric vehicle. So their plan is by 2040 there won't be any new fuel-based vehicle on the market, and they want to scrap all the remaining vehicles, fuel-based vehicle, within 10 years line or so. So the expectation is by 2050 or so, all the vehicles should be electric. So transport sector is one of the key sectors generating very large number of carbon emission. If you look at carbon emissions generated by number of sectors, transportation sector is one of the topmost. And then they say how carbon emission will look like. So if you're using a battery vehicle, it's a 97. If it's a plug-in vehicle, hydrogen fuel cell, petrol-based, so how does this vehicle generate carbon emission? You can also look at here in terms of how much end-of-life production, fuel consumption for petrol one, for hybrid, for plug-in hybrid, and for complete electric vehicle. So that's one of the reasons companies, the government is pushing, and companies kind of considering this as an opportunity to, to expand in this market. So the UK government also pushing charging stations. In order to bring electric vehicle in the market, you need charging stations, yeah, and you need really enough charging stations. So currently, so again, it's I guess 2 years back data. It's not the recent, maybe last year data. So they deployed on 32,000 locations with X number of devices and connectors. So we got two type of charger. One is public, like general charger. One are rapid charging. So they are chargers that can quickly charge the batteries. Some are more regular, but then there's always a trade-off when you say charging. Rapid charger will quickly charge, but then reduce the life of your battery. Faster charger doesn't mean they are good. Yeah, some regular charger takes time, but they don't destroy your life of the battery. But then you always have option depending on your need. Yeah, so it's not like you always go for rapid or ultra rapid. You can go for a standard charger, but then if you need it at any point, if you're in a hurry or whatever, go for there as well. And then it's generally so how they have distributed across the UK within Scotland, Wales, and other part of the region. What are the drivers for e-mobility, which is the electromobility is a part of the smart grid. Now people start thinking once we got electric vehicle, this has direct, indirect impact on the grid. Of course, when people start charging it requires a lot more energy, right? You are replacing fuel-based electricity in a way. So there's a need to revisit smart grid itself. and try understand what will happen when we have electric vehicle in the market. As of now, we don't have too many around the world, but then you can realize a point where you see every other vehicle is electric vehicle. Right? So the system that we have in place as of now will completely change in the future. There will be a lot more demand of energy. And then we are talking about different energy sources we've already talked about. Transportation sector, one of the key thing is they want to develop those kind of mechanisms that are sustainable. And carbon emission, they can reduce the carbon emission. But these are sustainable. It should not be like every 5 years you start thinking, oh, it's not working, let's think something else. Yeah, it's about the vision. So the countries, companies, they have a long-term goals. They wanted to see these kind of thing in next 10 years, next 20 years vision. Yeah, things takes time. So it's just the concept, but then the concept evolves as we go in time. Now people are saying you got battery to run your electric vehicle. But what kind of battery we are talking about? How long you can go with that? How often you need to charge those battery? What is the life of that battery? How much is going to cost for people? Yeah, if the electric vehicle of the charging is too high, possibly people won't be able to switch it. They will still prefer fuel-based, whether it creates carbon emission or not. Countries like Western, they might afford because per capita there's a high income, but compared to countries in developing countries, it might still not be able to, might not be possible quickly to do this. So the reduction, CO2 reduction through EV, complete urban mobility through integration of individual and public transport. So people are also thinking not just individual vehicle, but having EV with public transport. You got electric buses, electric trucks, electric trains. Even start thinking if you can have electric planes for a small distance, you know. Infrastructure independence is once you. So now in electric vehicle, basically we are talking about electrical system and mechanical system bringing together. So system becomes much more complex. People who are electrical engineer might not be able to understand mechanics of it or the other way. And then cybersecurity people don't understand any of these. But then when you bring system together, you need to look into this, what are the security and mechanical side, electrical side, learn things and think about the solutions out of it. So we got 2 projects I just wanted to highlight. So we have two large projects. One is with the US, University of Illinois in the US, and in University of Chicago, with the clean energy and equitable transportation solutions. The whole point, they were kind of looking into those strategies they can develop in order to support electric vehicles. How can they have clean energy that can reduce carbon emissions. Even they are also looking into if they can use hydrogen-based fuels as a replacement to the current fuel, petrol, diesel based. And then we are kind of having cross-cutting themes of cybersecurity. When they've developed this kind of an approach and system, then what could be the potential cyber threats to the environment within the system, and what are the issues that we see, and what kind of recommendation we want to put in place. So it's a $10 million project for 5 years, 4 years, I guess, 4 or 5 years. Then we have another project with being Australia for UK Australia Center on secure Internet of Energy. We say supporting EV infrastructure at the edge of the grid. So the whole point is when you have electric vehicle, this kind of thing, you are also making certain decisions. Right? When you plug in, so the whole environment is pretty dynamic. As a vehicle, you can go and plug in anytime. You can plug out anytime. Right? It's not like you have, there's a mandatory, if you charge, you have to charge for 10 minutes or so. So the environment is very dynamic, and for smart grid operators, utilities, they need to develop those kind of plans to understand, to kind of derive the forecast predictions, what will be the demand in this region. Right? Nowadays we do this based on what is the requirement in terms of businesses, in terms of home residence. Right? But now you also need to think electric vehicles. So you might have some commercial stations, charging stations, or you might have a plug at your home where you want to charge it. So the demand will change once you have electric vehicle and different type of vehicles in the market. and then we will be generating a lot of data out of it. So what could be that data? What are the devices that will connect? What are the so the whole idea was when you connect to and possibly it's just the very early stage. We can say for electric vehicle, but it might be in the future you might have that when you're connecting to a vehicle. People were also talking about what about the privacy of data? If I'm connecting my vehicle to a charging station, maybe I'm giving my personal information, or maybe information related to my car. If I'm making payment, possibly I'm giving some of my details as well. So people were thinking, can we come up with something called anonymous payment system? So you can payment, but then the company who are collecting your payment able to verify they have received the payment, but they should not be able to figure it out who are those people. Now the companies, the operator can also learn few things. Let's say if they know that you go to a particular place because there's only one charging station in the region, you go there, you charge your vehicle, and based on the status of your battery charge, if it is 50% charge, 100% charge, they can derive that information. You can travel that long only in this region before you recharge your battery. So those kind of information can also help attacker to target individuals, and might also be giving some patterns when you go to a parking lot, when you go to a banks where there's a charging station. So that kind of information can also be derived that a person acts actually visiting those banks, those restaurants, and so on and so forth. Yeah, so they are also collecting some kind of information without the consent of the actual person. So there are kind of serious consideration about cyber security, not just data. So data privacy is one of the issues, but then you have powertrain of EV. So this is a subsystem that push your vehicle forward in a way. So what could be those cybersecurity issues or scenarios that are critical in nature that can compromise the safety of the vehicle? Charging infrastructure. What if someone having a fake chargers, and malicious thing collecting information and impacting the grid? So people also started thinking about what if there are multiple. In the future, might be scenario where you have large number of vehicles connecting to this, and the whole point is to destabilize the grid. Yeah. So let's say there's a capacity of X amount that a company can produce or can support at a time, but then the capacity is much larger. What is happening in the Prayagraj these days? Yeah. There are a lot of people coming. There's no capacity, overcapacity. Something like this happened with this environment where the grid's realizing the sudden overload. Yeah. And then we don't have really kind of tools to support it, or interdependency kind of based on attacking vehicle from the grid side, attacking through batteries or the other way, destabilizing the grid. Issues around communication, label security. When you are able to access some of the component remotely, then what technology we are talking about? Is it Bluetooth? Is it RFID? What data being sent to the control center or other units? What level of security there, and so on. And of course, there are a number of protocols which are there. Right. Yeah, so these are the typical scenarios. So I'll skip this. So this is a typical ICE engine, internal combustion engine. So it's generally run by one of the fuels. It could be petrol, diesel, gas, and so on. Then we have something called hybrid electric vehicle. As I said, it's a combination, batteries and one of the fuels. Then you have plug-in hybrid vehicle. What does it mean? So car can run entirely off store electricity, but then for shorter distance. But for longer distance, you need to use gas or whatever. And then you got full EV, where you have really powerful batteries where you can travel longer distance in one go. So there are a lot of research has been done. So again, these subsystems are really the whole systems. There are a lot of research being done on something around battery management system. So maybe we can think of, you go to a parking lot, you charge your battery, start charging it. Now, how long it's going to take? If there are only few charging stations, the way you see the queue for petrol, diesel, you'll see the similar queue in the future, even larger queue where people are just waiting for hours to get some to charge their batteries. So there's another concept coming up saying, can we replace the battery rather than charging it? So similar to, you just go there, get the new batteries, attach to this and take this off. So they can pre-charge it. They all are pre-charged. Just go there and detach this and attach the new ones, and then go from there. Will it help? If that is the case, then you don't need so many charging stations. Yeah, so there's a kind of some argument around why we are having so many charging stations. Might be this technology might not work in the future, or this will create always that people are struggling to get their charging their batteries. So if you can pre-charge it, might be helpful. But then pre-charge means you need extra batteries that can be charged, the system that can charge batteries in a massive scale. Yeah, so let's see how it happens, but it's kind of a long way to go. There's another concept called V2G and G2V. So grid to vehicle, vehicle to grid. Now we were talking about, until now, we were talking about charging it. Now there's also a concept, people say, can we also discharge it? So there's a model. So we were talking about saying peak on, peak off time. At any point, if you see there's a lot of energy demand, obviously prices will be higher. So there's also something called dynamic pricing model. Every few minutes you get to see this is the current price if you want to charge your vehicle. If you're charging your vehicle when there's already peak demand, prices will go up and up and up like the stock. Yeah, people will buy stocks and price goes up. If you're charging at peak off time, charging will be lower. The price will be lower and you need to pay lesser. So, and also the concept, when there's a requirement in peak hours, more energy, if my battery is charged, can I discharge it to the grid? Can I give that energy to the grid? Can I sell it to the grid? So the grid can utilize it for some other purpose, or someone else can charge. So what kind of profit I can earn if I discharge it? What's the benefit I have? Yeah, so there's a charging and discharging kind of concept coming up. But again, all these are kind of concept as of now. There's no discharging as of now. But in the future, you might see when you see when things are not manageable, the kind of energy the companies are producing not good enough for all kind of vehicles to charge it. So that could be the case. So it's as I said, bi-directional energy concept is coming up. People start thinking about it. If I'm going for holiday for a week, I want to discharge it. If I 100%, I want to keep it 20% and then discharge 80% so that I get some profit out of it, whatever. And you can decide at what time you want to discharge. So all those concepts are coming, but they're still, then people are talking about something called vehicle to vehicle, vehicle to infrastructure communications. When you have connected vehicle, you need, so there are something called roadside equipment, what we call it, RSU, yeah, RSU something. So roadside unit, sorry, RSU, we call it. So roadside unit will collect information from the vehicle, process it, or maybe sending it to some server, processing it, and then sending all the vehicles to manage all the things. So there's a vehicle to vehicle communication, vehicle to infrastructure communications, vehicle to grid communication, grid to vehicle, and so on. So there'll be a lot of data going around. And the question is how you handle data, how you think about the security of the system. So vehicle to consumer, vehicle to charging point, vehicle to grid, and there are several use cases that we can look into V2G system. So this is how it looks like. You got a vehicle, you got a charging station. Now charging station getting electricity from the grid in some way or the other, right? So if we can't supply here, you won't see electricity, you won't see energy here. And depending on how many number of vehicles are there, needs to compute, calculate what energy requirement is there. And that calculation, that data will feed back to here. to understand how much supply we can give, because we have certain supply for committed supply for example, businesses. Yeah, so they sell electricity to businesses at much higher rate compared to households, and those are their profit model, business model. So obviously they will prefer to sell it to businesses with a higher rate compared to other people's. But then if they need to support this kind of infrastructure, can they fulfill all the demand? Can they supply that energy? If yes, then at what price, and so on. So again, we talk about IEC 61850, which is substation protocol. Then we got another is called IEC 15118 for electric vehicle infrastructure. Again, we are not going to detail, but then just give you an idea to look. There's something is called aggregators. So the role of aggregator is to collect information. If I'm saying there are 10 number of vehicles, there are 100 vehicles sending their information, there's some server or device called aggregator, especially in the case of advanced metering infrastructure. When you're sending data from households, smart meters, we got a device called aggregator that collect data from every household and then sending it to the control center to process it. So aggregators are the intermediate devices, but the point is, where would you put aggregators? What is the capability of aggregator? How much data it can collect? What kind of security they have? If you're putting a security on smart meters, electric vehicle, whatever, but if your aggregators are not secure or someone can compromise them, they can compromise all data. And then aggregator are the one can possibly have some capability. They can pre-compute something, make certain decisions at local level, but then obviously they need to send the data back to the control center that can make decision and understand the big picture, right? Because those are the people sitting at control center can only understand the big picture. If you're working at local level, charging station level, you won't be able to understand it. Right, so you got vehicle, you're connecting to charging station, in vehicle station connecting to the grid, they are aggregator collecting information and exchanging here and there. Then we have several substations. So for example, here we call it EVSE, which is electric vehicle supply equipment, a charging station that you see, the kind of device you see, and there are some other setups. Then we see this one is called electric vehicle communication controller. So you need some controller to control the system. You got some links, connections through home plug green physical, which is called HPGP, is a power line communication. So power line communications are more dedicated power lines that supply electricity. So there will be two lines, two connections, one for power line, power connection, other one will be communication line, exchange of data and controls, and then the actual supply of power. Yeah. And obviously you have battery management system. This is the whole system, how you manage the batteries, charge, discharge, control things. And then you got HMI, human machine interface, where people to control things when, because at local level you also need to control the whole system. And then we have just kind of some view around IEC 15118. So this plot talking about several type of vehicle. For example, mild hybrid, full hybrid. Then you got battery electric vehicle. Then you got extended range for vehicle that can travel longer with electric batteries. Then you got NEV, new vehicle, or sometimes we call it neighborhood electric vehicle, which are used for shorter distance. Then you have PHEV, plug-in electric vehicle that you can charge, but you can travel up to certain distance. But then it also supports gasoline. They're not purely hybrid. They're not purely electric vehicle. But then you have FCEV, fuel cell electric vehicles. There are also concept of can we run them with hydrogen. Right. So I guess the transport minister in India, Mr. Gadkari, yeah, they also talk about something called methanol. So we are developing some, ships and cars and so that they will run on ethanol. So there are different fuels people are trying that can support. Obviously, we know the electric vehicle battery-based system might be the more. This is again, if we are doing this in a massive scale, this becomes much cheaper in a way for individual. At the same time, also reducing carbon emission. But then in order to fulfill that supply, we might still be relying on other sources. So we are also looking into what are the other sources that can reduce the carbon emission compared to fuels that we are using as of now. And this will also help us in a way if you have less dependency on petrol and diesel. Yeah, because as India doesn't have enough, petrol, diesel, we mostly kind of import it from Saudi Arabia, from Russia, US and other countries, Iran. So in a way, we will be having less dependency on those. And based on demand and supply, those prices will go up and down. If you're able to produce by your own, you have less reliability. Otherwise, you have to bring that oil and keep reserve oil. There's a lot of storage for those, to supply it when there's a shortage. As I said, there are aggregators in between. Sometimes there are also security concerns or privacy concerns, mostly saying there are aggregator collecting your data. Possibly they have access to this, and they can misuse your data. So how you anonymize information before sending it to the aggregator to collect, and at control center or at billing unit, more importantly, how can you de-anonymize it, so that you get to see, you're generating the bill, but then who are the people, household name you want to send the bill to. So there are some methods in terms of how you can anonymize and de-anonymize data for the purpose. So you anonymize, send it to the aggregators, aggregator collect all the information, send it. But then at some way you have to relate that data for the billing purpose. So you got battery vehicles, they are aggregators, so we call it local aggregators, LAG. The local aggregator depending on the region. So you got one aggregator covering a wide area, similar to the tower, the way a cellular network works. And the multiple aggregator within a wider region, they all are collecting information, sending it to control center and so on. And then people are still thinking, how can you authenticate those vehicles? How can you understand? So for example, if you are thinking around a cardless payment system, that means before you start paying, before you start charging, they wanted to know whether you have enough balance or not, so that the amount will automatically be detected from that source. So some kind of security system needed. But also, if there are few devices, they can authenticate one after another. But if there are large number of vehicles, people are developing solutions around batch authentications. Can you authenticate multiple vehicles in one go? That might be more efficient way of doing so. So again, security requirement around confidentiality, integrity, access control, forward secrecy, which says if system is compromised now, it does not have any impact on the previous data. So in a way, if someone compromises your key as of now, they should not be using this key. It should not be able to decrypt, let's say, the data that you have encrypted in the past. That's why we always say every time whenever you need to do encryption, you generate new keys. In worst case, if one of the keys compromised at any point in time, your previous data is still safe. But if you're using the same key, once it's compromised, everything is compromised. That's why forward security. Mutual authentication means it's a bi-directional. So user can authenticate device should be able to authenticate user. So this was the problem with GSM. So when GSM came into we call it second generation, 2G. Yeah. So there was issues around system, the network can authenticate user. As I said, they have inbuilt chip and keys and so on. So it's in the background it happens. But then there was no way the user can get a sense that you are connected to the right network. And at that point on, there were several redirection attack were happening. So what is redirection attack? As a fake tower, I can create a fake tower with more strength to the signal. And generally, when you look at the signal, you want to connect to the signal which is the highest strength, right? And you are connecting to that tower, giving your information, and they're using your password to actually connecting. So you end up with connecting with a rogue device and doing whatever you are doing, they are capturing in a way. because there's no way you could verify whether you are connected to the right network or not. But then in 3G, they fix it, so on and so forth. The security issues around people can eavesdrop, understand what kind of level of encryption or security is there. There could be replay attack. People can hold your messages and reuse them. There could be packet capturing, tampering, spoofing, data block, denial of service, jamming. So those kind of all situations are possible to look around. So it's just this last lecture for today. Yeah? So, okay, so if you like, we can. Okay, just let's this slide and then we'll stop. So as I said, we are talking about, so now if you compare this environment where we have a substation, where there are a number of devices, but these devices are static in nature. Devices are not moving anywhere. They are not dynamic. You have already deployed, you know how many devices you got, and you have a model solutions for that. Now thinking about the electric vehicle scenario, where the whole picture is very dynamic. A vehicle could be part of the network, cannot be a part of the network after a few minutes. Vehicles are moving. They can charge here at this point in time, half an hour, 1 hour, they can charge somewhere else. So the whole system dynamic has changed. You cannot apply the same solutions in the dynamic environment. You need to develop those solutions that can handle the dynamic environment in terms of the need. As you have need in that point of time, you need to develop solutions that can handle those kind of situations. So mobility and dynamic participation bring new challenges for identification and authentication while a battery vehicle is moving from one area to another. The data itself may reveal sensitive information for both individual user and group of users, which makes local aggregators become main attack target for adversary. Because if you know there's an aggregator that collects all information rather than attacking individual device, it's better to target aggregators, right? End-to-end secure data communication is required. Again, when we are talking about a scalable system like this, whatever you are developing in terms of solutions, your solution should be very efficient because they're going to apply on large-scale systems. Yeah? So it's a computational load and communication overhead also bring challenges when secure solutions are to be designed. Both are very important in optimal performance security trade-off when application of security solutions considered. So what is called communication overhead? And what is computation overhead? So in a rough understanding, communication overhead, simply how many bits you are transmitting over the network. That is the communication overhead. Computational, whatever computation you are making on devices, on resources. And every device might have different capability, what you can compute, what you can store, based on that. So let's stop here. Let's go for this as well. So battery status related privacy. So as I said, sometimes we are sending some personal information or some information about your device. For example, charging status of your battery. If somebody knows that you have 50% of your battery, they can figure out how long you can go, right? Preference in terms of companies also wanted to understand the behavior preference of the user so they can customize, because they need to forecast. If they understand the energy requirement, patterns, behavior, it will help them to understand. Now there are certain, now people used to classify using machine learning, for example. You got data and then you classify. If we are talking about, let's say, home appliances, you can classify and kind of give some understanding what type of device. Now the research has been so advanced, even if your data is encrypted, there are machine learning algorithms that can classify those appliances over the encrypted data. Yeah, they're collecting encrypted data. They can run the machine learning model. They can still predict that you have a kettle in your home, you have a television, whatever. And that is somehow giving some additional information to the attacker, despite of the fact your data is encrypted. Yeah, so traditional methods are actually not working in a way. They're leaking some information. So local aggregator should not be able to ascertain battery vehicle accept decline. So whatever decision you're making, aggregator should not be able to learn anything. Yeah? Now this person always come and spend 15 minutes. Not like that. They should not be able to identify who are those people and so on. Location related privacy, you're going to a particular spot, your aggregator might capture that. So battery vehicle may move around different areas. Local aggregator can only obtain battery vehicle general group attribute without detailed identifiable information. And generally when you go to other area, rather than they process your real identity, they should be processing something called pseudo identity, which is very similar to when you go to a remote area with your cell phone. So there's something called IMSI number. Have you heard IMSI? International Mobile Subscriber Identifier, something. So every SIM card has a unique IMSI number. Yeah, so you're connecting to your local network. Through that identity number, they process it. When you go to roaming area and you don't want to reveal your IMSI number to them, so the system automatically derives something called TMSI, temporary number to that reason, so that they assign a temporary number, do everything, but then when it comes to verification, they can connect to your home area to verify it. Okay, so let's stop here, and we'll do the lab exercise in the afternoon. Thank you very much.